Hey guys, welcome back. Let's talk third law today. It's Mrs. Webb here. So Newton's third law is probably a law that you guys have actually heard of in the past. And it states that every action has an equal and opposite reaction. And this is also known as contact forces. So for example, if we were to push on a wall, okay, and I'm going to call my person A, and then I'm going to call my wall B. So object A and object B. If you push on that wall, the reason you don't fall through the wall is because the wall is returning that force that you're pushing into it with an equal and opposite force. And that equal and opposite force is balancing the force that you're exerting so that you don't go through the wall, so that your net force is zero, right? And so this red arrow here is my force of A, my person, pushing on B, the wall. And the wall is returning that force with another force that comes from B, the wall, and is being exerted on A, the person. Okay, so that's the whole premise behind these third law problems. If I push on something, it will push back on me. If I pull on something, it will pull back on me. That's the whole premise behind third law. So I've got an example here for you. And for this example, we have three blocks A, B, and C. A force applied of 20 newtons is applied to A, right? And if you guys know, if we push on this block, eventually we're going to get all of these blocks sliding as one big unit, right? So remember when we did second law, we talked about how if we had multiple objects, like the people in the canoe, or the two blocks that were attached by a string, or our pulley system, or our Fletcher's trolley, whenever we had something where there were multiple objects, but all those objects were moving as a single unit, when we looked at it in terms of second law, we could assume that system of multiple objects was just one big object, right? So when we drew our free body diagram, we drew it as one large object. We showed our force applied, moving to the right. We had our force gravity, and we had our force normal that was equal and opposite to the force gravity, right? And we knew that in the y, or in the perpendicular direction, our net force was zero. And in the parallel direction, the parallel to the surface direction, that net force was equal to the sum of the forces, and the only force in that parallel direction is my force applied. Now, remember that when we expanded this, we knew that we weren't moving at a uniform rate. And so we wrote this as mass times acceleration. And because we were assuming that this big block was all three of those individual blocks A, B, and C, we said that the mass was the total mass of the system that was being accelerated. And that was equal to the force applied. And so the total mass of all three blocks was 9.5 kilograms. The acceleration was plus 20 newtons because I said right was positive. And we were able to calculate that the acceleration was 2.1 meters per second squared to the right or forward. Okay, probably better to say to the right. Now, that's if we're dealing with it in terms of a second law problem. And typically in this situation, we would be looking for what is the acceleration of the total system. Because now what we want to do is we want to look at this problem in terms of a third law problem. We want to find what is the force, the contact force that is being experienced here from box B, because as soon as I apply this 20 Newton force, box A is going to press into box B. And there's going to be an equal and opposite force that's pressing back on that A block. And then block B is going to press into block C, and there's going to be an equal and opposite force that's going to press back into block B. And then block C is just going to move. right? And so we wanted to, when we're doing a problem like this, we need to figure out first off, well, what's the acceleration of the entire system, so that now we can focus on these individual forces, these contact forces, which are a third law problem. Okay, so we figured out our acceleration. Now we're going to look at it in terms of third law. So when we look at third law, we can't assume that we're looking at one massive system that's moving all together. We have to look at the individual blocks. So we're going to have to draw individual free body diagrams for all of the blocks. So for block A, I draw my free body diagram, and I know that I have my force applied being applied to block A. So I'm showing that force applied being applied to the right. I know that as soon as block A has this force applied on it, it's going to press into block B. So that means that block B is going to push back on A. So there's going to be this leftward force from block B resisting block A's force applied. And then we'll have our force gravity and our force normal, which are balanced. For block B, there's no force applied on block B, because the force applied is specifically being, the person's hand or whatever specifically on block A. So what's actually going to get block B moving is the fact that block A is exerting a force on block B. And as soon as block A exerts a force on block B is going to start to slide into block C, which means that block C will return that force on block B. So there'll be a leftward force from block C resisting block B's force. And then for block C, well, block B is pushing it, so we get this force B on C, and there's nothing to the right of block C, so there's no force being returned. Now, for all of these scenarios, we know that in the perpendicular direction, there's nothing happening. It's a net force of 0. So we can just make our statement and leave it at that. Now we have to make the decision of where do we start here? How can we calculate these forces? So I know that I was given force applied. That's the only thing I have. I don't have force of B on A. I don't have force of C on B. I don't have force of A on B or B on C. So I have to start here, because this one is the one that only has one unknown variable. So I'm going to set my system of my force equation. I've got force net parallel is equal to my sum of the forces, force applied plus force B on A. And notice that I've said that right is positive. Now the force applied, the force net is going to be, because I do know that this object is accelerating, the force net is going to be equal to the mass of block A times the acceleration. And that's equal to force applied plus force B on A. Now I know that block A has a mass of 2.0 kilograms. We calculated the acceleration to be positive 2.10526 meters per second squared. I know that the force applied is positive 20 newtons. And I'm solving for force of B on A. So if I rearrange this, I get the force of B on A is negative 16 newtons, or 16 newtons to the left. Now, remember that if the force of B on A is negative 16 newtons, or if the magnitude of the force of B on A is 16 newtons, then that means that A must be exerting an equal and opposite force on B. So that means that we've also just solved for this force of A on B. So now we know that force of A on B is 16 newtons to the right. So I'm going to set up my equation for the net forces in this parallel direction for block B. So we have force net parallel is equal to force of A on B here plus force of C on B. And that's all we've got. Now I know that the net force is the mass of block B times the acceleration, and that's equal to force A on B plus force C on B. And I know that the mass of block B is 4 kilograms. It's also accelerating because they're all moving at the same rate. It's also accelerating at positive 2.1052 meters per second squared. And that's equal to, I'm going to keep my unrounded number, positive 15.78947 newtons plus force C on B. If I solve for force C on B, that gives me 7.4 newtons left. And if I know that force C on B is 7.4 newtons, that means that force B on C has to be equal and opposite. So force B on C is 7.4 newtons to the right. Okay, so we've just found out each of the individual contact forces and the acceleration of the entire system. Okay. So that's in terms of a Newton's third law problem. Another example, which is a fairly common example, would be something like this, where we have a series of train cars. We know that the mass of car A is 2 kilograms, the mass of car B is 2 kilograms, the mass of the engine, car C, is 4.5 kilograms. And this time we're being told the acceleration. It's 0.75 meters per second squared forward or to the right. And we want to know what is the force applied. Okay. So we have to start, because we know acceleration, we don't need to start with a Newton's second law problem where we look at the system as one big mass. Because we're looking for the force applied and we already have the acceleration, we're going to start looking at this in terms of a Newton's third law problem. So we're going to draw the free body diagram for car A, B, and C. Now, car A back here, car A, the only reason car A is being pulled is because car B is pulling it, right? So the engine is pulling car B and car B is pulling car A. Okay? So what's happening here is there's a force of tension on this connector rod that is coming from car B pulling car A. And that's the only force being exerted in this horizontal direction. Now, on car B, there's a little bit more happening. There's a tension force here on this rod from C, car C, pulling on B. But remember that A is going to resist that pull. So it's going to pull back on car B. So there's going to be a force of tension from A resisting B pulling on it. So we have the force of tension of C on B and the force of tension of A on B. And then on car C, well, there's going to be the force applied. The engine is propelling the car forward. And as the engine's propelling the car forward, B is going to resist that motion. And so B is going to pull back on C. So we're going to have a force tension of B on C. Now I'm going to explain that again, but actually I want to explain it the other way around for you. So imagine our train is stopped. Okay? So all of these objects, if they have inertia, they're going to resist that pull. They're going to resist the urge to move. They're going to want to stay still. And so as soon as the engine fires up and it applies a force in the right direction, it's going to start to move. But all of these cars are going to resist that motion. So as soon as this engine moves, it's going to start to pull on this rod, but car B is going to resist that pull. It's going to pull back. And eventually car B will be overcome and it'll start to move. Now car B will start to move and it'll pull on this rod, but car A has some inertia and it's stationary and it's going to resist the pull of car B. Right? And so that's why we're getting these tension forces that are working against the other car. So that's our free body diagram. We know in the perpendicular direction there's not much happening. It's not like we're levitating or sinking into the ground. So now we have to figure out, well, what do we need to solve for? Overall, we want to solve for this force applied. But the problem with starting with this block is that I don't know what the force of tension from B on C is. And then I can't start with this block because I don't know what force tension C on B is, and I don't know what force tension A on B is. So I've got too many unknowns. So my only option is to start here with force tension B on A. So I'll set up my equation. I've got force net X, and that's equal to my sum of the forces. And the only force here is the force of tension from B pulling on A. And I know that the car is accelerating, so I'm going to have mass of A times acceleration is equal to force tension from B pulling on A. The mass of car A is 2 kilograms. The acceleration is positive 0.75 meters per second squared, and that's equal to force tension from B on A. And if I solve, I get the force tension of B on A is positive 1.5 newtons, or 1.5 newtons to the right. Now remember, if B is pulling on car A is going to resist that pull. It's going to pull back on B. So that means that the force of tension on A, from A pulling on B, is going to be equal in magnitude but opposite in direction. So I know that this force here is going to be 1.5 newtons, but it's going to be left. So now I know this, so I can solve for this, right? So we're just moving our way down the line. My force net parallel is equal to the sum of the forces, so force tension C on B plus force tension A on B. My net force is equal to the mass of the B car times its acceleration, and that's equal to the force tension of C pulling on B and the force tension of A pulling on B. If I fill in my values, I get 2.0 kilograms plus 0.75 meters per second squared, and that's equal to the force of tension from C on B plus minus 1.5 newtons. And we get that the force tension from C pulling on B must be positive 3.0 newtons, or 3.0 newtons left. Now, if that's true, if car C is pulling on car B with a force of 3 newtons, then car B must resist that pull with a magnitude of 3 newtons, but in the opposite direction. So that means that the tension from B on C is 3 newtons to the left. So now I know this force, and I can solve for the force applied. So we've got to do one more problem. We have F net parallel is equal to force applied plus force tension B on C. This time F net is mass of the engine, car C, times acceleration. That's equal to the force applied plus force tension B on C. Plug in my numbers, I solve for force applied, and I get the force applied is positive 6.4 newtons, or 6.4 newtons to the right. So these problems, guys, kind of general rule of thumb is if you don't know the acceleration, the first thing you need to do is you need to look at the system like a Newton's second law problem. Look at it as one big unit in order to solve for the acceleration. Once you know the acceleration, now you can break that system up into its individual parts, and you can figure out what are the contact forces in between each of the objects. Okay. So definitely, this is probably the law that gives people the most trouble because there's a lot of stuff going on. So give it some thought. We'll give it some practice in class time. There's a worksheet online called Trains and Boxes that we'll be working through. If you want to start on that ahead of time, please, by all means, feel free. And as always, bring your questions to class. I hope you're doing well, and we will chat very soon. Take care.